everybody. My name is Drew, and I'm a PhD student at Stanford University. And today, I would like to talk with you about how graphs, compositionality, and structure can be leveraged to improve our capabilities in the domain of visual question answering. For those of you who may be less familiar with it, visual question answering is a fascinating task that interleaves three research areas: vision, language, and machine learning. And they are all combined together in order to solve one challenging but straightforward task. Given an image and a natural language question about the image, our goal is to provide an answer. The visual question answering task has an array of applications. First, it may allow us to interact more intuitively and effectively with vast amounts of visual and unstructured data that's readily available to us through the web, especially at this age. Second, it may help us improve human-robot interaction in a variety of situations, such as exploratory or emergency cases, or help analysts in reviewing surveillance data, or may even help the visually impaired in the daily lives. Finally, as a challenging multimodal problem, it allows us to test in an integrative way our full AI systems and is a challenging and exciting research problem. So let's look at the following image. What do we see here, and what does the machine see? So current visual recognition models have no problem at all to recognize the various objects in the image, such as the dog, or the couch, or the person. But we see much more than that. We are able to see the full context, even a story. Not only can we tell that the couch is torn up, but we can also infer that the dog has probably done that. We can see the look of guilt on his face. And we can also infer from the posture that the person is not very happy. And we can see the whole story immediately. And so, in contrast to machines, we are able to see things in context and understand interactions and subtle relations between objects or events. We easily make abstractions that focus not on the raw signals and statistics, but on the high-level semantic knowledge, which we then can apply to another new situations and generalize. We can make inferences and fill in the details when there are gaps in the information and make new conclusions. And overall, in contrast to machines, we are able to do not just learning, but also reasoning. What does it take to build models that are capable of these things? So let's start from what we have right now, right? Neural networks. These are very powerful and robust models. They can take in anything, any image or data or signal, and they simply provide an answer, the prediction. And it's all very simple and very convenient, but we don't know exactly how they reach it. They're basically a black box. And this has very serious problems, because as a result, neural networks, for instance, can confuse correlation with causation, learning instead the wrong associations between things. And in contrast to how people learn, they need a lot of data for training, and they fail to generalize to unseen conditions. And finally, as I just mentioned, they are hard to interpret. So in my belief, what we need to do is to look for ways to open up the black box. And one way potentially to do that is by adding structure that will make things more modular and interpretable. One particular structure that is useful for visual reasoning tasks is called a scene graph. And in this talk, I would like to show you how scene graphs can be a useful abstraction that help us in tasks that involve both vision and reasoning. All right, so let's define what exactly scene graph is. So the main resource for scene graphs is called Visual Genome. That's a data set from a couple of years ago. It has 100,000 images that all come with annotation of structural representation of the knowledge in them in the form of a graph that has three main components. First, it has objects. Any visual entity in the image. This can be person, apple, sky, or beach. Any sort of entity. All of these objects are annotated by attributes, properties of these objects. This can be any property: color, material, shape, activity, position. And finally, we have relations between the objects. These are like the edges between the nodes, the objects. And these can be verbs such as eating or holding, special relations such as on top of or behind, and comparatives. Scene graphs, like these, are very useful intermediate representation that is both structured and unambiguous. And they have a variety of applications, and I would like to show you a couple of examples. So one example is image captioning. So as I said, like the common way to do image captioning is to build a large neural networks, black box, and start from the image and pass it through the network and get a caption. But a recent work shown that if we first predict the graph from the image and then use the graph to predict a text, a description, we get better descriptions that are both more detailed and cover more information about the image. So this is one example when scene graphs are useful in making better tasks of, in this case, visual captioning. Another example is image generation. A recent work has shown that scene graphs can be used as an intermediate latent representations that help us make the image generation process more compositional. Basically, different regions in the image are conditioned on specific nodes, on edges, and thereby we are able to achieve more control over both the structure and the content of the generated images. So these are a couple of applications of scene graphs. And in this talk, I would like to show you two more applications, especially for visual reasoning and visual question answering. First, we will see how scene graphs can be used to build new visual question answering data set that has compositional multi-step questions over real-world images. And then we will see how we can build a new model for relational reasoning that can solve such compositional questions. All right, so let's start from the first one. So there have been existing data sets about VQA, and you can see here a few examples of such questions. And you may be able to notice that one of the main problems with this data set is that the questions tend to be too short usually and too simple. So you can see a few examples, like in this image, question can be, is this a dog? What color is the apple? Sometimes there are a bit more complex questions such as, what is the dog sitting on, or what is the person holding? But these sort of relational questions are very infrequent. So overall, questions in existing VQA data sets, they tend to be too simple, not relational, and definitely not compositional, because as you can see, they don't require several steps of reasoning to answer, only ask about one attribute or one relation. And another main problem about existing datasets is that VQA dataset is that they have very strong and dominant question biases. So for instance, if I ask you what color is the apple, usually the answer will be red or green. And usually tables are made of wood. And turns out that models can take advantage of all of these world biases and many times makes educated guesses without really looking at the image. In fact, experiments have shown that blind models that don't have access to the image at all just read a question and can answer an existing dataset more than half of the question correctly. This is really a serious problem about existing dataset because it means that they don't really test for visual reasoning. And we would like to have other datasets that are more robust to such gaming techniques and are more compositional. And that's exactly what we try to do in a new dataset that will be presented in next CVPR in a month from now that is called GQA. And what is special about our dataset in contrast to other visual question answering dataset is that in our case, everything is structured. Each of the image comes with a scene graph, a structural representation of its knowledge. And then we use these scene graphs in order to generate automatically compositional multi-step questions. And each of these questions come with functional program that represents its underlying semantics and is grounded back in the scene graph. So let's see a short description of how we can generate automatically this question. So basically what we need is two components, content and structure. The content comes from the scene graphs. We already talked about that. So these give the knowledge about the image. And then the structure, we couple this content with like a question engine that we've built that takes care of all of the grammar rules and synonyms and structural patterns to get questions. So I can give you an example of such pattern. Here is some probabilistic pattern. This is quite generic. You can see like what or which type do you think is the object attribute 1 or 2? This is quite generic. A question that corresponds to that concretely can be, what color do you think is the apple, red or green, if we instantiate each of these slots? And each such pattern is also a corresponding semantic representation that represents a series of reasoning operations that we have to do in the graph to compute the answer. So far what I described to you gives us a way to generate questions over the image, over the scene graphs. But we would like to have them compositional, multi-steps, not just simple. How can we do that? So basically, we look back at the graph and we try to traverse paths over the graph and use them in order to make compositional references. So I will give you an example. We can see the fries here in the image. One way is to just call it fries, but I can also call it in a different, more compositional way. I take it a bit to the edge, but I can call it also the food on the red object to the left of the small girl that is holding a hamburger. This is a quite complicated way to say fries. And if I take this reference and plug it back in the question pattern, I get the following question automatically. What color is the food on the red object to the left of the small girl that is holding a hamburger, yellow or brown? Basically, all I ask here is whether the fries are yellow or brown. But in this form of question, models can't just guess the answer anymore. They have to really look at the image, find the objects, and track the relations in order to compute the answer. So using this technique, we were able to create more than 20 million questions over 100,000 images that cover a variety of reasoning skills. I will give you a few examples. There are questions about relational reasoning, comparisons, questions about logic, like and, or, not. There are questions about spatial reasoning, and, as I said, compositional questions about multi-step reasoning. And you can see here a few statistics for the data set. So we can see that indeed it covers a variety of reasoning operations, and it also has different number of reasoning steps, like there are some questions with 2 steps, 3 steps, and even some questions with more, 4 or farther. So what we've seen so far is that we were able to generate data set with 20 million compositional questions over scene graphs that cover a variety of reasoning skills, and they are all generated automatically. I won't get too much into the details, but we also able to use this technique in order to balance the data set and reduce biases. Basically, we use the semantic representation that is associated with each question in order to do rejection sampling of the answer distribution conditioned on the questions, and in that way, we are able to make the answer distribution less skewed and less biased, and so that it has larger variety of answers. All of the details are in the paper, and I won't get into that too much. Another thing that we're able to do by having the semantic representation for the question and the images is to define new metrics that give us more information about the inner workings and behaviors of models. So a couple of examples. One is consistency. So by using the semantic representations, we're able to check whether models answer semantically equivalent questions in the same way, whether they are consistent or not. And another example is grounding. Because all of the questions are grounded in the scene graph, we can measure not only whether models provide the right answer, but whether they also look at the relevant area in the image. So overall, by having these new metrics, we're able to get more information, more insight about the behavior of VQA models. So this concludes this part of the talk about generating a new data set with compositional questions that are more balanced and have new metrics. And if you would like to find more information about that, you can find it in visualreasoning.net, and we also hold a challenge that will be presented in CVPR in a month in the VQA workshop, and then winners will be announced in the workshop. And so at this part of the talk, I showed you how we can use scene graphs in order to generate compositional questions. There is still one strong, big question that is left unsolved about how to build models that are capable of answering such questions. And so I'd like to show you just a brief overview of a model that we've worked on last year that is called MAC for ICLR 2018. Our goal there was basically to have a model, build a new model that is, on the one hand, neural and fully end-to-end differentiable, but on the other hand, it's explicitly and in transparent way performs a multi-step reasoning process in ways that are a bit similar to classic AI approaches. So let's see an example. Let's look again at the image and the following question. What is the red thing behind the black object to the right of the person? how can we build a model that answers such question? So what we do is several things. First, we look at the image, and we recognize all of the objects. We can do it by simple object detector. And then we'll take the question, and we pass it through a neural decoder that focus at every step a different phrase of the question. This will be different reasoning operation, and it will try to locate it in the image. So at the first step, it will focus on the word person, and it will try to localize it in the image, and will find the object of the person. At the second step, it will focus on the next phrase, the black object to the right of. What it's currently holding in memory is the person. So when it will look for the black object to the right of it, it will shift its attention to the black couch. And then we will repeat this process again. We'll look for the right thing behind what we currently have in memory, which is the couch, and we will find the apple, and this will be our answer. So in a bit more formally, we're able to achieve this by defining a new recurrent model that has a recurrent new cell that is called MAC that decomposes the question into a series of reasoning steps. In contrast to many other recurrent networks, we have two dual hidden states, control and memory, that run over the question in the image in parallel. The control tracks different phrases at each step from the question, and the memory accumulates the corresponding information from the image that corresponds to these phrases of the control state. We're able to achieve this. This is the structure of the MAC cell, and there are several units that interact with these two control and memory states. The control unit, as I said, tracks different phrases from the question, and then the read unit retrieves the relevant information from the image that is corresponding to the phrase, and finally, the write unit integrates this information from the read unit into an evolving memory state. And after we concatenate several such recurrent steps together, we are able to have a neural differentiable model that explicitly performs a transparent multi-step reasoning process. A nice byproduct of our model is that because we use attention for everything, probability distributions over the questions to get phrases and over the image to focus on different regions, we are able to visualize the whole reasoning process that the model undergoes while trying to answer a question. So we can see an example here for another data set that is called Clever, for another data set for visual reasoning. And again, we can see how the model every time focuses on different objects and different part of the question until it computes the answer. So this was a qualitative result, and we also have some quantitative results. On this same Clever data set, MAC performs very well, almost perfectly. It achieves, in fact, 99% performance, even overpasses human. On the new GQA data set, MACs perform more modestly with a bit more than 60%, where people get almost 90%. So for this new data set, there is still ample of room for further research to explore. So to conclude, in this talk, I showed you how scene graphs and structure can be used both to make a new data set of real-world visual reasoning and compositional question answering, and we were able to show how to build a new model for relational reasoning that is able to solve such questions. The two papers that I mentioned in this talk and described are Compositional Attention Networks for Machine Reasoning from ICLR 2018 and GQA from CVPR 2019. And thank you very much, and I'm happy to answer questions.
Thank you very much. Questions?
Thanks for the talk. So you said that in the GQA data set, like all the questions are automatically generated.
Right.
So they are all like, I guess, valid questions, but some of the questions look like really long and things that humans might not naturally ask. So are there any artifacts you noted, like while you're trying to, if you, for example, trying to train on the data set?
Yeah, so in making the data set, we actually collected the original patterns from the original VQA data sets in order to make them natural. And indeed, there are some questions that are complex and a bit compositional and maybe a bit non-natural, but many of the questions are also relatively natural. And we also took another steps in order to make question more natural, such as using large variety of synonyms and incorporate in variety of grammar rules to make everything like diverse and natural as much as we could.
Any more questions?
Yeah, simple question. Do you plan to release the code to generate the text, like this functional programs?
We don't release the code to how to generate the questions, but we do have in this part of the dataset all of the questions with the functional programs. So we provide the functional programs for all of the questions. The reason that we don't provide the code is that we don't want to let people do reverse engineering of the dataset and not need the image anymore. So we don't provide the code right now.
But it's basically like clever. It's like a clever code, just a kind of next level kind of scene generation,
So yeah, I mean, it can have applications, and maybe we can release some more generic, some abstract, just the essence of the engine. Yeah.